Welcome to Math with Mrs. Bibb. Today we will be discussing linearity, intercepts, and symmetry. You will find a link in Google Classroom to a Quizlet with these terms. Just like the last lesson, if you will please, go to Quizlet and fill in the definitions for these terms. Now we will begin the examples. Example 1. Example 1 asks us to identify linear functions from equations. So hopefully in the definitions of linear functions, you are able to tell by looking at these equations if these are linear or not. I just reread the definitions, and the definition did pretty well, telling you that there's no variable raised to, I think it said this. Now that I think about it, I'm not sure. Let's write it here just in case it did not say this. A linear function, we're going to write this in the middle, has no variable raised to a power other than 1. So the largest exponent is always a 1 in a linear function, which means, let me define what that means. If you have a variable in the denominator, that means you have a negative exponent, which means there's no variable raised to a power other than 1. This would be to negative 1, so that would not be linear. Also, you could not have the square root of x, because if you have the square root of x, that means you have x to the 1/2 power, which means that is not linear. Let's look at the problems. Oh, one more thing. It did say that an equation that could be written in the form y equals mx plus b. And that equation does fit those descriptions above. My exponents are positive 1. Now, let's look at letter A. Can I say that letter A fits all of those things that are in red? First thing I'm going to do, I'm going to rewrite that. F of x equals 6x divided by 3 minus 5 divided by 3. Those say the same thing. And so I would have f of x equals 2x minus 5/3. Do I have any variable raised to a power other than 1? No, x to the first power. And can this be written in y equals mx plus b form? Yes, f of x is the same thing as y. Y equals mx plus b. So this one is a linear function. For letter B, I have y to the first power and x to the third power. So that tells me that this one is not linear because of that raised to the third power. Moving on to example 2. It says determine whether each graph represents a linear or a nonlinear function. If the graph is a straight line, it is a linear function. Letter B is a linear function. If it is not a straight line, which I know students would say that this is a straight line connected to another straight line, but it has to be a straight line collectively. And so this one is nonlinear. And that's all you need for that example. For the next example, this says it's a real-world problem. We are looking at this word problem saying Michaela has started working part-time at the local hardware store. Her time at work steadily increases for the first 5 weeks. The table shows her total earnings each of those weeks. Are her weekly earnings modeled by a linear or a non-linear function? So, let's look at the table. And you can see the table written in two ways. We're looking to see, because to be linear, I'm going to write that down. To be linear, you have to have a constant rate of change. The y over the x has to be a constant rate of change. So the first thing I'm going to do is look at my x's. X is the weeks, y is the earnings. Are these increasing at a constant rate? Plus 1, plus 1, plus 1, and you should be writing this down as well, plus 1. Yes, they are. So my run, which would be the x, would be positive 1. Now let's see if these are increasing at a constant rate. I do 119 minus 85. That is 34. And then I do 153 minus 119. That is 34. Interesting. And then I do 187 minus 153. That is also 34. And one more time just for, and I'm just going to type that in the calculator, and you do not have to write the difference. But please write everything that I write down. 221 minus 187. That is 34. So this is modeled by a linear function because there is a constant rate of change. And I put this in what you would see in Desmos as well, and you would see that is created a constant rate of change, the same thing here. This is going up by 34 each time. This is going up 1 each time. So I've got a constant rate of change. For example 4, our instructions say use the graph to determine the x and y intercepts of each linear or nonlinear function. So remember, the x-intercepts are where it crosses the x-axis. Please write that down. I know it might be tiny. The y-intercepts are where it crosses the y-axis. Okay, so for letter A, the x-intercept is, it crosses here, -1, -2, -3, -4, -5. X-intercept is -5. The y-intercept, +1, +2, is +2. For letter B, I believe I have multiple x-intercepts. I've got 1, 2, 3, 4, 5. What are they? I'll start from the left. -1, -2, -3, -4. So I've got -4, -1, -2, -2, 0, 1, 2, 3, 3, and 5. My y-intercept is also 0. For letter C, my x-intercept is 0, and my y-intercept is 0. For letter D, my x-intercepts, plural, I see 1, 2, 3 x-intercepts. This x-intercept has a special name. It is called a double root. Make sure to write that down. The reason why it's called a double root is there are two solutions there. When a graph touches the x-axis but doesn't cross it, a double root occurs. So my solutions are -1, -2, -3, -3, -1, and 2. It is not necessary to write that 2 twice, but I'm showing you that there are 4 roots to this particular function, and 2 of them are the number 2 because that's considered to be a double root. Then the y-intercept Did I do that right? The scales, I hate when the way they change the scales. -1, -2, yes. But the y-axis is different. 4, 8, 12. So it's going by fours. So it looks like 8, 12. So 12 is the y-intercept. Moving on to the example 5. It says, interpret the meaning of intercepts. So we're going to look at that real-world example and interpret the meaning of the intercepts. First of all, letter A says, let me read the problem. Ricardo launches a rocket from a balcony. The table shows the height of the rocket after each second of its flight. Okay, so part A. Identify the x and y intercepts of the function that models the flight of the rocket. So the x-intercepts. Now, we do not have a graph, but remember, the x-intercepts means that y is equal to 0. If you have an x-intercept, then y is equal to 0. So when I look at this one, my x-intercept is 8 because y is 0. And then the y-intercept is where x is 0. So x is 0 here. This is my y-intercept. The y-intercept, I'm going to put where x equals 0, and the y-intercept is 15. So that's the x-intercept and the y-intercept. Now, for part B, what is the meaning of the intercepts in the context of the rocket's flight? I want to start with the y-intercept to explain the meaning. So the y-intercept, I drew a graph. The y-intercept, that's where x is 0. So where x is 0, the y-intercept is going to be 15. Now what does that mean? The initial height of the rocket before it is launched. So we can also say, there's another thing we can deduce from this. Ricardo launches a rocket from a balcony. So we could also say, that's one interpretation. We could also say the balcony is 15 feet off the ground. Okay, that's the y-intercept. The initial height, or the balcony, is 15 feet off the ground. For the x-intercept, I'm going to add to my picture up here. So as the rocket is flying through the air, Ricardo is recording, and I'm not making it go up steep enough, hold on. So as he's launching it through the air, he's recording the height. And then it comes back and goes down. This is your x-intercept. What would that be? So the rocket is flying through the air, and what happens right here? The rocket hits the ground after 8 seconds. That's the meaning of the x-intercept. The rocket hits the ground after 8 seconds. And moving on to example 6. Actually, no. Before we go to example 6, we're going to look through and we're going to talk about line symmetry. Let me grab a highlighter. We're going to talk about line symmetry. So a graph has line symmetry if it can be reflected in a vertical line. So looking at our graph here, look at this orange line. Oops, I'm going to undo that. Look at this orange line here. So that's our vertical line. And if you can reflect a point, and this is how I say that, point A is 2 units to the left of that vertical line. Point A prime, that means like the second A point, is 2 units to the right of that vertical line. So a parabola, this is a parabola. If you did not know, that's what that is. And please write that down. A parabola has line symmetry, and that line goes through what is called the vertex of a parabola. And you can choose points on the parabola. They're equidistant, which means the same distance from that orange vertical line. So that's called line symmetry. And then it says the line dividing the graph into matching halves is called the line of symmetry. So that orange line is called the line of symmetry. And now for the other type of symmetry. A graph has point symmetry when a figure is rotated 180 degrees about a point, and it maps onto itself. That means it would land on itself. So if you're looking at this cubic function, which is what that curve is, that blue curve is a cubic function. If you rotate that graph, that blue graph, 180 degrees, so if you rotate it 180 degrees, then it would map onto itself. So this graph would have point symmetry because the image of each point on one side of the point symmetry can be found on the line through the point, and the point of symmetry equidistant from the point of symmetry. So a cubic function has point symmetry, and a quadratic or parabola, a parabola specifically, function has line symmetry. So there's not much to write here. Just make sure you have those things highlighted or underlined that I underlined, and try to understand what that means. And we'll talk about it more in class. Going on to the next example. Example 6. It says identify types of symmetry. So when I look at this first function, would that appear to have point symmetry or line symmetry? Could I draw a vertical line down the middle and have points equidistant from each of that vertical line? No. So it does not have point symmetry, it does not have line symmetry. It has point symmetry because you could choose a point, you could choose this point and rotate that graph 180 degrees. So we could rotate it 180 degrees and it would map onto itself. So this one has point symmetry. Letter B. Can you draw a line down the middle and split that parabola in half? 1 unit, 1 unit, yes. So this one has line symmetry. Letter C. Can we draw a line down the middle and map 2 units this way and 2 units this way? No. So it does not have line symmetry, and I'm going to erase my line. Can we put a point here and rotate this graph 180 degrees and map onto itself? No. So this one has no symmetry. There's no line symmetry or no point symmetry for this one. So you cannot do that. No symmetry. And then for the last one, j of x equals x cubed minus 2, can you take a point, rotate this graph 180 degrees through that point, and land on the same, or map onto itself? And yes, you could. At 0, -2, you could rotate that graph 180 degrees and it would map onto itself. So this one has point symmetry. Moving on to example 7. Actually, no, I'm not going on to example 7 yet. We're going to talk about types of functions, even functions and odd functions. That's what we're going to do first. So, an even function. One thing for sure that I know about even functions, for even functions, the ends point in the same direction. Now that's the Mrs. Bibbs quick version of even functions. Ends point in the same direction. And so odd functions, the ends point in opposite directions. To test it algebraically, to show your work algebraically, to decide if something is an even function or an odd function, you do what I just highlighted in green. So I'm going to write that out, what you do. First, you substitute negative x in for x. So you evaluate that function by substituting negative x in for x. That's the first thing you do. Second, you have an even function if once you evaluate when you substitute, you get f of x. If you get the original function, it's an even function. You have an odd function if once you substitute negative x in, you get the opposite of f of x. But if you get neither of those, if it's not the opposite and it's not the same, then it would be neither. So I'm not going to write anything there, but it would be neither if it's not the opposite or the same. And I'm hoping that the last slide has examples for this. If not, I'm going to come back and do some examples. It sort of does. So I'm going to test. We're going to test my theory. See, I'm going to say this is an odd function. I'm going to say this is an even function. And I'm going to say this is an odd function. Odd because the ends are pointing in opposite directions. Even because the ends are pointing in the same direction. And odd because the ends are pointing in opposite directions. Now I'm going to prove that algebraically. I'm going to substitute negative x in for x. So in place of x, I'm going to put negative x. In place of x, I'm going to put negative x. And sometimes what my little theory is incorrect because sometimes the mathematics doesn't work. So let's go see if that happens on any of these. So I'm going to evaluate f of negative x would equal negative x cubed would be a negative times a negative times a negative, which is still a negative, so negative x cubed. And then negative 4 times negative x is positive 4x. So what I need to figure out is the original function is f of negative x equal to the opposite of the original function. So what's the opposite of x cubed minus 4x? Would be negative x cubed plus 4x. Is this negative x cubed plus 4x? Yes, it is. So this is an odd function. Let's look at letter B. To be an even function, f of negative x has to equal f of x. So let's see if that's true. So g of negative x would equal 2 times negative x raised to the 4th power minus 6 times negative x raised to the 2nd power. So g of negative x equals, I could do my exponent first. A negative times a negative times a negative times a negative is a positive x to the 4th. I'm going to put minus 6. A negative times a negative, because that's negative x squared. A negative times a negative is a positive x to the 2nd. So is this, I'll highlight, I'll use yellow, is this the same as this? Yes, it is. So it is an even function. Now let's try letter C. I think it's odd, but we're going to work it out and see if it is. We'll see if the mathematics works. So I'm going to do h of negative x. I'm going to have negative x raised to the 3rd power plus 0.5 times negative x raised to the 2nd power minus 3 times negative x raised to the 1st power. So let's do what I know. Negative x cubed would be negative x cubed. 0.25, negative x squared would be negative x times negative x, which is positive x squared, which does not change this plus sign to a minus. And then negative 3 times negative 1x is positive 3. So what I want to know is h of x, or h of negative x, the same as the opposite of h of x. So if I take the opposite of x cubed, I get negative x cubed. Yes, it is. If I take the opposite of plus 0.25x squared, I get minus 0.25x squared. Is that true? No. So this one is neither even or odd. Neither or none. That's the answer to that last problem. And I think that's it for this section. I hope you have a wonderful day.